V curves of synchronous machine. I say machine, V curves can be drawn for motor operation and also for generator operation. That curves also called as constant power curves. Constant power curves. This characteristic also called as constant power curves. So requirements that mentions about a experiment. During the experiment we keep something constant. For example, machine is motor or generator, it doesn't matter. And then frequency constant, voltage constant, and active power of the system is constant, is kept constant. If it is generator, electrical output of the generator must be kept constant. If it is motor, shaft load of the motor must be kept constant. During the experiment, load current, one-phase armature current, is observed by changing field current of the rotor. Okay, so vertical axis represents armature current, and then horizontal axis shows field current. Voltage is constant, power is constant, and then let's start. Power is equal to 0.1 times of its rated value. Okay, let's start here and then adjust field current, and then you will observe such a change. Power is 10% of its rated power, and then let's say 0.5 of 50% of its rated power, and then let's say 0.8 of rated power. During that operation, you observe there is a minima point here, and a minima point is moving towards the right, and the minima looks like no load curve. If you excite more in generator mode, that means generator is operated as a inductive generator or lagging current generator, if it is generator. In midpoints, machine is operated as pure ohmic. Pure ohmic. I mean power factor is unity. By decreasing field current from its certain value, that means machine is operated as capacitive generator mode or leading current generator, leading current generator. The left hand side of the no load curve belongs to capacitive operation of generator, and right hand side belongs to inductive operation of the generator. Then it is reversed in motor mode. Here is capacitive motor mode, here is inductive motor mode, and again all minima points are on power factor unity, which is pure ohmic mode. Okay, it means power factor changes by changing field current. In fact, we have already examined this topic. When you change, we have examined this topic here in active and reactive power control lecture. If you change field current, machine will change reactive power. So since you keep active power constant, the ratio of reactive over active is phi, which is phase angle. So cosine phi, which is power factor, will change. When you change field current, machine reactive power will change, phi will change, power factor will change. In excess excitation, over excitation, a machine can go inductive generator or capacitive motor operation. In under excitation mode, you observe capacitive generator or inductive motor operation. So let me explain this thing by using phasor diagrams. Okay, we have already examined active and reactive power control. Here is real axis. That is the positive rotation direction of phasors. And first assume that machine is operated as generator. So generator equation, EF is equal to V1 plus JI1 XS. For the simplicity, let me omit array and then draw V1 and then current. Let's say current is ohmic, and then JXS IXS is here. So as a result, that is the EF, and that is the delta. Now, ladies and gentlemen, keep power constant means there are two asymptotic lines. One is EF times sine delta constant. The other is I cosine phi constant. Because terminal voltage is constant, remember active power, voltage times current times cosine phi. So voltage is constant, current times cosine phi must be constant. You can study these in these video lectures. Okay, and then here are two asymptotic lines. I1 must be on this line. Here is I1 cosine phi asymptote, and then here is another asymptotic line, which is EF sine delta asymptotic line. EF must be on this asymptotic line, and current must be on this vertical asymptotic line. Now, ladies and gentlemen, I over-excite the machine, I increase IF. In such a case, EMF will increase, flux will increase, and then EMF will increase. When EMF increases, here you see, let's say EF, and then there is a new vector, which is Ji prime, let's say prime XS, and here's a new delta prime, and here's a new current vector, which is 90 degrees lagging than this guy. And again, current vector must be on this asymptotic line, which is I1 prime, and here you see phi prime, and here you see phi was 0, and now it is lagging. Houston, it is lagging. And then apply under excitation flux will decrease, EF will decrease. Okay, here is the under excitation. EF double prime. There is a vector completing the circuit, which is J I double prime XS, and then there is a new current vector lagging 90 degrees. That's one. Those are perpendicular. And current vector must be on these asymptotic line. So here is I1 double prime. Here is phi double prime. What you have observed during that changes? The minimum current in the armature is in ohmic operation. Theta. Here it is, minimum current. Minimum current. And then, when you apply over excitation, here you see EF will increase. And then machine go under lagging current operation or inductive operation. And magnitude of the current will increase. Again, inductive generator operation, and the magnitude of the current will increase. Or if you apply under excitation, EF will decrease, and then as a result magnitude of the current again will increase, but in capacitive mode. The phi double prime is leading. Phi double prime is a positive, and it has a leading property. Leading. And here you see under excitation the current again will increase. Here are two limits. When you apply under excitation, you observe a dramatic delta increase. Delta you know must be less than 90 degrees, so there is a stability limit. Here is a limit must not be exceeded, so that is stability limit. And then when you apply over excitation, here you see there is a current. Here's the current, but to make over excitation you have increased field current, so IF squared times RF cause some copper losses in field coil. There's a heating, and then as a result here's an increasing armature current. 3 times armature current squared array cause some copper losses in armature, and again there is an overheating in armature. So the right hand side here is overheating limit. So machine must be operated in that region. Here are inhibited regions due to machine limits. You also know that synchronous generators can deliver power and reactive power. So if power capability will increase, there is a smaller range for the reactive power. Here you see a smaller moving area for the reactive power. Here would be a narrow band for the reactive change. That is the V curves or constant power curves of synchronous machine. As a second method, I use phasor diagrams of generator. Someone can also use phasor diagrams of motor. The similar results will be reached, and the results will be reversed. For example, in excess excitation, machine operates in inductive generator mode, but if it is operated as a motor, machine go under capacitive operation. In under excitation, machine operates capacitive generator. If it is operated as a motor, machine behaves as inductive motor. That is the V curves. You can find some similar figures, V curves of synchronous, let's say, generator, machine, motor. Here you see some images. Looks like what we have done. Here you see stability limit, constant power and power factor unity. So we like ohmic loads. Ohmic loads cause minimum heating for the machine. You see minimum current is drawn under ohmic loading. V curves. Stability, overexcitation or heating limit, power factor unity. There's also inverse V curves or power factor curves. It is not in our scope right now. V curves. Okay, bye bye.